All right, the moment you've all been waiting for, our first endeavor into officially talking about the derivative within calculus. So, derivative is going to represent the slope of a curve. It also is going to represent the slope of the tangent line. Because we're talking slope, we can think about the derivative as a rate of change. And specifically, it's going to be an instantaneous rate of change. I apologize for my handwriting on this computer, but hopefully you guys will be okay with it. All right, so let's get into it with your notes packet. So, definition of the derivative. Well, we've talked about slope being a rate of change, and we know that to find slope we use the letter m, and we represent that with our change in y over our change in x, which would be the same thing as y2 minus y1 over x2 minus x1. So if I have some curve, we'll call this purple curve f of x, and I wanted to find the slope, I can use a secant line to help me represent that. So a secant line, remember, intersects the curve at 2 points. So we'll use this as our secant line. And I could call this x1, and this would be x2. So then this would be y2 and y1. And we could find the slope between those. Instead, I'm going to call this a and this b, in which case this value up here is the point b comma f of b, and this point right here is going to be the point a comma f of a. Someone is taking their garbage out outside of my window. I apologize if you heard that. So the slope of this red line we could write as y2 minus y1 over x2 minus x1, and that would represent our slope. So again, a secant line approximates the rate of change of f of x. We saw this in preview week a little bit. So if I wanted to figure out the rate of change of this purple line, how is this purple line changing, or this purple curve, I could use the red line, the secant line, to help me in figuring that out. Well, if we want to talk about the slope at various points along a curve, so again, that purple curve, that was f of x. So here's my curve happening again, and here was that secant line, and I had a and b, okay? Ideally, what I would want to happen is if we let a, we call that x, and we're going to let b be called x plus h, because we're talking about this distance right here. We'll call that h. All right. Well, if I start then with f of b minus f of a all over b minus a, that was our slope of the red line. And I replace it now with my new definitions of what a and b are. I'm going to have f of x plus h minus f of x all over x plus h minus x. Alright, well, thinking about that, if we wanted to close in the distance between a and b, it means I would want this distance h between them to be closing in and be closer to 0. So I'm going to put the limit as h goes to 0 of f of x plus h, I'm ditching the color coding, hopefully you can see that, over, in this denominator our x's are going to cancel, so we're going to be left with just h. And this again is what we call the limit definition, because it has the limit in it, of the derivative. If you remember from preview week, we use f prime, or f with a little apostrophe, of x. So as h goes to 0, instead of having a secant line, if we close in this gap, right, so as I move closer and closer and closer and closer, eventually I'm talking about a tangent line instead, and now this represents the slope of the blue line. Whereas this one up here was just the slope of the secant line, estimating the rate of change of that purple curve. Alright, so here's some pictures so you can see it. There are 2 applications on our website, but if you go to our site, right here under secants, tangents, and graphs, oh my, you can mess around with those on your Chromebook and see a little bit more hands-on. But really what's happening here is that we have our point P, right? And as we move P closer and closer and closer to Q, this distance h is going to close in. And now, instead of having a secant line, we get closer to having a tangent line. Alright, so find the slope of the tangent line. So slope, rate of change, derivative of the tangent line at this curve, f of x is equal to 3x squared plus 4. Well, we know that f of x being equal to 3x squared plus 4 really means f of fill in the blank equals 3 times fill in the blank squared plus 4. The point 216 does lie on this curve because f of 2 is equal to 3 times 2 squared plus 4, in which we get a result of 16. Well, we want to find the slope of the tangent line, so we're going to use our limit definition. F prime of x is equal to the limit as h goes to 0. It's really important that you write the limit every time, because without that limit in front, we're not talking about a tangent line. We'd be talking about a secant line. And we want to close it in. Alright, well, our f of x was this function right here. So I'm going to plug in x plus h everywhere I see an x. Minus, then this is just my function on its own. All over that h value that was still there. Well, when you plug in h going to 0, you get 0 over 0, which means we need to keep going. And our keep going in this case is going to be cleaning up our algebra. So I'm going to have 3x squared plus 6xh plus 3h squared plus 4 minus 3x squared minus 4. Try to do that algebra on your own. Make sure it matches up with mine. And now some stuff's going to cancel. So those are gone. And those are gone. And this numerator has an h in it, so we can factor it out. And we're going to have h times 6x plus 3h all over h. H's are going to drop now. And the limit as h goes to 0 of this function, this part's going to go to 0. And we are left with f prime of x equals 6x. So what that really means is that the slope of f of x is always 6 times the x coordinate. Okay, and remember our f of x was 3x squared plus 4. Well, that's all well and good, except we want to define the derivative, or the slope of the tangent line, at 2. So I want f prime of 2, which means I really want 6 times 2, which means f prime of 2 is equal to 12. Now, that represents the slope of our tangent line. So if we think about this parabola, graph it in purple, there's our f of x. And we were interested in what was going on at the point 2, 16. Here's our tangent line. What we just found is that the slope of this tangent line is equal to 12. So I could go a step further and I could actually write a full equation of this tangent line. Well, what's needed to write the equation of a line? You need to have a point. Oh, lovely, the point 216. and you need to have a slope. Oh great, our slope is 12. So I can write that equation in point slope form. Y minus 16 is going to be equal to our slope times x minus 2. This is an okay equation of a line as a final answer. Alright, so I'm going to have you stop this video, or this video is going to end. I'm splitting it up into 2 videos. So our next topic is going to be differentiability, which means when can you take the derivative. So we learned how to take the derivative, right? Limit definition, plug in all of your functions, x plus h, clean up your algebra, plug in whatever value you're looking for, and if necessary, you can actually write the full equation of a line, although this one only asked us for the slope, which we would say is 12, so we did a little bit of extra work. So now we're going to talk about, well, when can you take the derivative? Are there any times where this limit definition, or this way of finding the derivative, might the derivative not exist?